Hello and welcome to the gea-hilge Center of Competence for Hygienic Pumps. My name is Oliver Harder and I'm a product sales manager for Hygienic Pumps. Today we want to talk about NPSH, why it is important for selection of pumps and what influenced the NPSH value during the process. Later on we will show on our test rig a video with the result of this theoretical part. So NPSH, net positive suction head, is calculated out of two NPSH that we have when we want to select a pump. One is the NPSH available. This comes from the unit, your installation, and the NPSH required. This is what the pump requires to transfer the liquid, because the pump can only handle liquid and not vapor. So we need to keep the liquid as liquid, and this is required by the NPSH. For the NPSH calculation, from your installation, we need the pressure from the height of the tank, for example, so the static one that gives us, plus the one from the atmosphere. This is normally given, minus the pressure from the vapor, minus the pressure from the friction losses. So everything you install from the tank to the pump, as valve, bends, measure equipment, strainers, all lowers your pressure F, because it increases the pressure F and this lowers the complete NPSH. So this is the factors that we have. The static pressure, if you have a tank, here's your liquid, and here it goes to the pump. So this is your static pressure. For the calculation, I would take the bottom of the tank when you want to empty the tank. And if you have always the same level in the tank, you can go on that level. Then you have the pressure from the atmosphere, that comes from here, from the atmosphere. Normally in our area where we live, 1 bar, 10 meters. And then you have the vapor pressure that works against this. And you have the friction losses that lowers your NPSH. The pump now also requires a certain NPSH, which is NPSH required. And to have a safety factor, NPSH required, is always available plus 0.5 meter, because we have some factors that are always changing, like the vapor pressure, for example. Vapor pressure can change dramatically the complete calculation, because for water, for example, at 20 degrees, we have a vacuum pressure of 0.23 meters. If we heat it up to 90 degrees, we have 7 meters. So then you change this factor dramatically and you come into NPSH value. And this is not what we want to have. Also, the friction losses needs to be calculated. Each valve that you add later on will have influence on the friction loss pressure. Also the pump, when you speed up the liquid by entering the pump, you speed up the liquid and then you lower the pressure. This comes then also on the negative side from the NPSH available calculation. And this is then the reason for cavitation, because the liquid starts boiling or vaporization here in this area, and then we got what we see later on in the video on the test rig. So if NPSH A is then too low, we have some possibilities to change. We can higher the tank, we can increase the diameter of the pipework to reduce the friction losses, we can reduce the elbows, for example, we can also fill the tank with a higher level, or we can reduce the valves or some installations that we have. We can try to lower the pump to a lower point in the installation, and we can increase the pressure in the tank so we have more atmospheric pressure then. This pump is being forced into insufficient suction by manually closing the inlet valve. As a result, the net positive suction head available, the NPSH-A, has dropped below the pump's NPSH required. Watch the formation of vapor bubbles inside the glass housing. This occurs because the pressure of the pump inlet falls below the liquid's vapor pressure, causing the fluid to boil locally and create vapor pockets. As these bubbles move into regions of higher pressure, they collapse violently. Every implosion produces a tiny shock wave that strikes the impeller surface. Over time, this leads to erosion, vibration, and a noticeable reduction of pump performance. Cavitation isn't just noisy, it shortens pump life and can lead to unexpected downtime. Also note the mechanical seal. It's running with insufficient lubrication even after suction conditions return to normal. To prevent it, make sure the NPSH available always exceeds the NPSH required, ideally with a proper safety margin. Good systems design and correct pump selections are essential to avoid these damage effects.